This video, we're going to show that there is no simple group of order 132. If you're into watching mathematical proofs like the one I'm about to give, you should subscribe to my channel, as this is all we do on this channel. Now, let's go over what it means to have no simple subgroups. A group is not simple if and only if all of the CLI subgroups, or the number of CLI subgroups, is 1, or actually one of them is 1, and P is 1, or and Q is 1, etc., or and Z is 1. One of them has to be 1. So now we are going to prove this by way of contradiction. We are going to assume that none of these CLO subgroups have just 1. Okay. Now 132 is 12 times 11. 11, of course, is prime. But 12 is 4 times 3, which is 2 squared times 3, which tells us there will be at least one silo subgroup, some silo 11 subgroup. There will be at least one silo 3 subgroup, and there will be at least one silo 2 subgroups. Now, we are going to assume that the number of silo 2 subgroups is not 1. We are going to assume that the number of silo 3 subgroups is not 1, and the number of silo 11 subgroups is not 1. And of course, we're going to arrive at a contradiction. Now, other than 1, what can N2 be? Well, it must divide everything but 2 squared. That is, must divide 33. Well, that implies that the said N2 can't be 1. It's either 3, 11, or 33. For this criteria. Another one is that N2 must be congruent to 1 mod that number. Well, that just implies odd. This is all the odd numbers. When you divide by 2, the remainder is 1. That's the definition of odd. So N2 is either 3, 11, or 33. Other than 1, the number of silo 2 subgroups is either 3, 11, or 33. Let's hold on to that. Now let's do the same thing for the other prime, N3. Remember that the size of the group is 2 squared times 3 times 11. For N3, we just don't look at 3. That is, N3 must divide 4 times 11. That implies that N3, remember, it's not 1. Either it's 2 or 4 or 11, 22, or 44. Also, N3 must be congruent to 1 mod 3. That is, it's 3 more than numbers on the 3 table. I mean, some numbers on this 3 table are 0 and 3 and 6 and 9 and 12. Oh, I'm going to add 1 to each of these. When you add 1 to 0, you get 1. We don't want that 1. You get 4, you get 7, you get 10 and 13 and 16 and 19 and 22. I can skip a little bit. You get eventually you get to 37, 40, and 43. The only numbers on this list and this list is, well, they both have 4, They don't have 11, they don't have 2, but they also both have 22. Okay, so what we conclude, and only 22, what we conclude is that N3 is either 4 or 22. I may have said 2, but 2's not in this list. Okay, so that's what N3 can be. What can N11 be? Remember, the size of the group is 2 squared times 3 times 11. To know what 11 divides by, N11 divides by, ignore the 11. What's left is 12. The numbers that go into 12 other than 1 are 2, 3, 4, 6, and 12. But also, N11 must be congruent to 1 mod 11. Well, you have the 11 table, 0, 11, 22, and you add 1. This number 23 can't be on this list because it's too big. So this tells me that N11 is in this set. N11 is in this set that contains the number 1 and it contains the number 11. I meant to say 12. And we're not including 1. Well, 12 is the only number in both lists. This implies that N11 is exactly 12. Okay, wonderful. Now, N11 equals 12 implies that there exist 12 silo 11 subgroups. They're all disjoint except for their identity element. Take any two of these 12, they will intersect only in the identity element. That means the number of non-identity elements from these 12 is 12 times, well, they each have 10 distinct ones. 10 times 12 is 120. Remember that our group is 132. Have that in mind. Now, we want to get a lower bound on how many elements. Because if, for example, I use 22 for the number of silo 3 subgroups, and ultimately, when I add 120 to the number of elements in these 22, sure, I may get more than 32, 132. Well, you may say, well, that doesn't imply that any of the ni's equal 1, because I didn't use the smallest one. I'm going to use the smallest ones. N sub 3 equaling 4. That implies that there exists 4 silo 3 subgroups, all of which have 2 non-identity elements, which are different in each of the 4 silo 3 subgroups. So, the number of non-identity elements from these 4 silo 3 subgroups is, well, there's 4 of them, and they each have 3 elements, but one of which is always the identity. So they have a total of 8 distinct elements between the 4 silo 3 subgroups, and if you think about it, the 12 silo 11 subgroups. That's because the order of these subgroups is 11 for the non-identity elements, and the order of these are 3. That is, every non-identity element in any of these Silo 3 subgroups, the order will be 3. Well, no element of order 3 is an element of order 11, and no element of order 11 is an element of order 3. That means these 20 and these 8 are distinct. Let's keep a running count. So far, we have 120 plus 8. That's 128. You know what? You can add one more. That's the identity element. That's 129. Okay, but you know what? In this case, it's okay to just stay with 128. Now, let's talk about N2 subgroups, or the number of Silo subgroups of order 2, or Silo 2 subgroups. There's at least 3 of them. Okay? If N2 is 1, there's only 1. That implies that there exists one Silo 2 subgroup, each of order. Remember, the order of the group was 2 squared times 3 times 11. So the Silo 2 subgroups are each of order 4. Well, what does that tell us? That means that the okay, so let's say this. Since N2 is bigger than 1, N2, I think we said, was 4. That's bigger than 1. Let's write. Okay, so since N2 is bigger than 4, I didn't say that there was 4 elements yet. Let's move this down. Okay, so this implies that the number of non-identity elements equals, well, we're saying temporarily that there's 1 of them, and they're all of order 4. Now, this time I'm going to count all 4, because I'm going to count the identity element. This is 3 non-identity elements plus the identity element. So that's 4. This implies the total number, let's write total. The total of non-identity elements is bigger than, because I use too small of a number, is bigger than 120 plus 8 plus 4. That's 132. There are more than 132 elements in this group that only has 132. That's a contradiction. 132, or let me use my language. More than 132, more than 132 is bigger than the order of G, which is 132. That can't be. So either, since we got exactly 132 when I let N2 equal 1, either N2 is 1, or N3 is 1, or N11 is 1. One of them is 1, and that's a contradiction. What does it contradict? We said at the very beginning, assume that none of them are 1. And if any one of them were 1, which we just concluded, that means there's no simple group of that size. And as a result of that, that completes the proof. If you like watching mathematical proofs like this, consider subscribing to my channel. Click the like button. Please leave a comment. Tell your friends, family, and enemies about my website. Hopefully I'll see you guys in the next video. Thanks for watching to the very end. Keep watching and learning. See you next time.